I'll start at the. So, guys, everybody, welcome to session 5 for Mojo Solutions and Services Course 1, LTE, UMTS, and DAS Design. So, before we jump into session 5, which today we'll discuss distributed antenna system design. We'll discuss the workflow and procedure and requirements. All of that will use without Ibwave. Our next session will be in detail, and in the next session we'll have complete details of Ibwave and how it works. In today's detail, it's the reason Ibwave is not included because there before you can move on to Ibwave, there are a lot of concepts which you guys need to grasp and understand in order to do the DAS or distributed antenna system designing. Distributed antenna system is also called in-building systems. Sometimes it's also called IDAS or ODAS or venue planning. So whatever it's called, it's basically distributed antenna system. So before we jump into this session today, I'll like to give you guys a recap of what we have been doing so far and where have been. If you guys remember this flow or process diagram from session 1, you guys should remember that we discussed that this is a very important diagram and whatever we do is pretty much depends on this a lot. So if we can recall, we said we start our design with the nominal design requirements. This is true for both DAS and Ibwave. We in our macro part where we had sessions about LTE macro design and UMTS macro design and then the RFDS preparation. For macro we have completed this journey till here, till RFDS. So we started for, as far as the macro goes, we have completed this journey from here to here. Okay, we did not go into the design requirements initially, but during the process we understood what are the design requirements are for any macro system. We studied about we had the separate session for ATOL for LT and UMTS. We reached over our initial RFDS and the final RFDS, how the RFDS is prepared. So if there is anything missing in the RFDS, then we go back and we do not consider it final RFDS. Once final RFDS is done, we go back to the ATOL. So we had a separate session about ATOLs for UMTS and LTE, so we know how to operate ATOLs. We understand a lot better the design requirements to design a network. And we know how the RFDS, what kind of RFDS and how to prepare RFDS in general. So this was the whole journey from design requirements to RFDS or final RFDS preparation for macro, both for LTE and UMTS, which we have completed so far. So in the process flow, we also remember that RFDS usually is based per site, it's not per technology. So if one RFDS contains both LTE and UMTS, we also saw that. But on the planning level, it's done separately. LT planning is done separately, and UMTS planning is done separately in ATOL. RFDS is same, but when we'll jump to the RNDCIQ, we'll find RNDCIQ is per technology. For LTE, it's separate document, and for UMTS, it's separate document. For LTE and UMTS, so that's what we know. The reason for the recap is the process pretty much remains same. Okay, the process pretty much remains same. Okay, in both the cases. So this was our first. This slides is from our first session. So the process pretty much remains same. Okay, so we all So now we'll start from the design requirements and understand the design requirements. So right now what we are doing in this first session is to understand the design requirements for DAS better before we jump, because in case of DAS, it's simpler to understand the design requirements. You don't have to go through the process. So we'll first understand the design requirements, then in the next section we'll study Ibwave, and then we'll go through a session of RFDS for DAS sites, final and initial, and I believe we will able to complete the final RFDS for DAS sites and the overall R&D CIQ in one session. We'll see how it goes. So this is a recap of the flow which we are following throughout. We discussed it in very high detail in the first session. So for macro, we have LT and EMTS, we have completed our generative final RFDS. For our DAS sites, we are starting our journey once again. So this is a recap for the process. Now I want you guys to recap for what is the DAS sites and how they work before we jump into DAS sites. So yeah, step remains 3 for 1 to 3 for DAS sites as well. And what is the DAS site? This is what are the distributed antenna system or IDAS example in pictorial view to give you guys a good view. So how they are installed inside the building. They can be installed outdoor as well. So these are some of the diagrams we went through. These are the diagrams. How does this is called the floor plan, which we will study today. This is the prediction example we have. This is the ODAS or outdoor DAS conceptual diagram. This is the design diagram or schematic which we will study today. And this is for different vendors before. So it's a very quick view for our DAS review, in fact, not the initial view, review before we jump into the DAS design itself. So let's start with today's session. And what we'll be doing again, we'll be going through the distributed antenna system design, which will include link budget calculation or schematic calculation, which will design the process flow, and which will include the design requirements and the basic concepts for Ibwave power calculation. Okay, so we will not use Ibwave. We'll not talk about Ibwave, but we'll talk about the terminologies used in Ibwave. So in next session, when we jump to Ibwave, we'll already be familiar with the terminologies and the overall function of DAS. So far, I assume everybody can hear me well, right? Okay. Yes. So, well, design methodology and link budget concept will be discussed. We will have a very good insight about the DAS design requirements after this session. Remember, DAS is also called distributed antenna system. If it's indoor, it's called IDAS. Outdoor is called ODAS. Indoor IDAS system is also called in-building system or IBS, or they are also called venues when we are doing tuning and optimization of those sites. So don't get confused with all these names if somebody is talking. It's the same thing. And we are covering all of these things in our course. Okay, in DAS design, previously the challenge have not been the design itself, but to communicate the design to different teams who will implement it and who will install it. So in order to communicate well, you have the process should be there and all the teams should understand the process. So there is a workflow which we'll be discussing. Ibwave, which is a tool for planning of in-building sites or DAS sites itself, basically, the reason Ibwave became so successful was not without it could not be done, but it allowed to do the calculations very easy and communicate those design to the design team very easy in terms of what kind of hardware equipment is required, what is the cable length is required, and what will be the cost according to that. All these things, IBV made it very easy to plan. So ease is one of the big factor of success of IBWave besides it, technical aspects, which are, in my personal opinion, are not the strong suit of IBWave. So what we'll be going through in this whole sessions to come, our outlines of our topic is we'll have a DAS engineering introduction, which we have already from session 1, which we reviewed just now. We'll see the objective. Design workflow is very important, and design workflow details step by step, which we'll be going through, are very important. Floor plan, continuous wave testing, equipment rooms, location design. So all these consideration and flow we have to consider. What are the design details required? What are composite power, pilot power, and power per channel concepts? Very important, these three concepts for designing IBWave in for designing DAS anywhere, especially in IBWave. So we'll be learning DAS, align the procedure and workflow, highlight the decisive factor to determine if the active system is unavoidable, cable length determination method to specify design details and required by operator for each task. So most important thing anywhere usually is to highlight the decisive factors to determine if the active DAS is unavoidable. So there is a process which we can use if we have to install active DAS or not, or the passive DAS is good enough. Usually what I have seen in USA market, they always install active DAS. Okay, reason being the cable installation quality, because if you are not installing active DAS, you will have to install longer coax cables, and maybe they are not able to achieve the quality of installation. That's why, or other factors. But usually everywhere where even if it's not required from technical perspective, you'll see in USA market operators have guidelines to install active DAS. So this is a national guideline usually to install active DAS. So that's how it works in USA market. So don't get confused if I'm telling you the procedure of deciding when to go for active DAS or passive DAS, and that process is not followed in market in US, but market otherwise. For example, in UAE, Dubai, that was strictly followed, and I believe it still is strictly followed in 2006, 2007. That was the determining factor. Like it was evaluated a lot better than in US market, which I have seen so far, that when to install active DAS and when to install passive DAS. So it depends on the markets as well. But this process highlights the method or process to see if you should install active DAS or passive DAS. But in some markets that is strictly followed. In other markets they say no, just install active DAS. Let's go. That's how they are done. So let's go to the general flow before we jump into the details of this flow. We have a floor plan by marking of floor layouts, which is basically this one, which is our step 1. Floor plan or antenna design and marking of floor layouts. We mark them. Okay. We mark antenna there. This arrows you see are an example of antennas, directional and omnidirectional antennas. So we say, okay, we need the coverage. We just open a layout and see, okay, this antenna's coverage with the ERP of 0 or 1 or 2 can be, our requirement is -5, -50 or -60. For our CP, for example, we'll say, okay, we'll install one here, one here, here. So at this stage, they are installed based on your perspective where you can get the good coverage. But when you run the propagation, you or the EIRP comes out, and then you run the prediction of propagation in IBWave, you have a better idea how does it look. Okay, so this is the first step. Basically, after that, on-site continuous wave testing. So we'll see how it is done, what is continuous wave testing and why it's done. Equipment room location, and this is a important step. Like, where do you select your equipment room? Okay, if you select your equipment room very far from the antennas, for example, in the basement, then it's not good. Okay, if you select your equipment room, uh, because there will be a lot of cable losses between you and then between the node B and the antenna, and your EIRP criteria will not be met. So you will start losing. So you have a design. Then you start, once your equipment room location is decided, you will have to prepare for schematic or design plan, where you will calculate the whole link budget or EIRP with respect to CPH or uh, the power per channel or composite power. You have a cable measurements per antenna, link budget as passive system, the ERP. So you, based on the room location, design schematic, and cable lengths, you can calculate EIRP per antenna now. If your EIRP is going below the threshold, we'll discuss what can be our thresholds for LTE and UMTS. We'll discuss that. If it's meeting, then we'll implement a passive system. If no, we'll implement an active system. If no, before we can go for the active system, we do the reevaluation of, for active or passive, and we try to negotiate the room location closer to the antenna locations from the building owners, and do the power budget calculation as well if possible. So if we re-effort to decrease the losses and bring node B closer to antenna, if that's true, then we will implement a passive system. No, then we'll have a design plan using active components, and link budget EIRP calculation per cell is done. Again, once you implement active system, you should able to meet ERP calculation. You should, if you don't, you will have to go and redesign, but usually that is not the case. Active system, you meet the EIRP threshold, and you implement the active system. So that is the workflow. I was saying in US market, usually they don't do this revaluation phase. They directly go for active system. Okay, so these are the major steps, around 8 in number. We'll be going in details for each step. So this was our first step when we start planning. What we do, we have a layout plan. In case of Ibwave, we will import this in our Ibwave tool. After importing this, we will scale it in Ibwave, but otherwise, if you're doing it manually, you will open the layout plan, which is a AutoCAD diagram, and you'll mark your antennas. Okay, so marking an antenna is done in a way that we will always try to mark antenna on the corner. Why? Because like this antenna can cover the here and cover here. It's cover in both. It can cover in both direction. It can cover in this direction, and it can cover in this direction. Okay. So similarly, so this is an important antenna position. Usually this is installed over here because over here there are elevators or lifts. So there's a thought process behind this marking of antennas. It's not done randomly. There is a stairway or walkway, and by installing antenna over here, I can cover this hall and this hall, this area of this hall as well. This is a omni antenna, so its pattern will be rounded. Okay, this is a directional antenna, so its pattern will be lobe. So I can see it can cover pretty much. So similarly, I install antenna over here. There seems to be elevator place over here, so you can give a coverage to the elevator and cover this whole area. So this is covering over here. Just to avoid any holes, you install one antenna over here, so you have a good coverage. So reason over here, maybe there is an elevator and they want the coverage in elevator, so they install one antenna over here, one antenna over here, and this is covering, this is elevator area, so they are covering that from both the directions. This is a lobby hall with the elevators to make sure all the lobby is covered very well. Similarly, they are pointing the direction over here to cover all this area because there may be some stairways or something which needs to be covered. Okay, so there is a thought process behind why and how these antennas are placed initially. Okay, usually we don't have to use directional antenna, but we can. It's an option, like it's used over here. But we should. These layouts are drawn to the scale. when you have a layout on paper or in Ibwave, the scale is very important. So you can know what is the distance between these two antennas, and Ibwave do the cable length calculation based on this as well. So looking at over here, you understand that there is some thought process which is when you start to mark antenna on the paper or put antennas on the Ibwave. You drag and drop the antennas on the Ibwave. There is a thought process behind it. Okay, so it's done according to that, which I tried to explain. So once you are dropping down the antenna, okay, you may come and see, okay, what if I install antenna over here? Okay, what will my signal inside this place? Okay, you can come and question this. What will be your over here? What will be your let's say inside here? What will you be coverage? Will be your coverage? You don't know that until the system is installed. You can know that until the system is installed by using a continuous wave testing. What in the continuous wave testing you will be doing basically, it's in continuous wave testing, you guys will be basically uh, come we'll install a transmitter, which is a test transmitter, okay, and test transmitter will be transmitting at a power, ideally at the same frequency on which we want to install our DAS system. And what we'll do, we'll install it over here, okay. We'll install our at the place where our antenna is, we'll install our test transmitter over here, and we'll have a receiver, which can be a scanner or which can be a UE. If your test transmitter is a dummy, let's say a UMTS transmitter, you can measure your, or a GSM transmitter, you can measure your signal over here and see how much is the path loss, because you can calculate the losses. Okay, so you know you're transmitting 40 dBm power or whatever, and you're getting over here minus 60, it's okay. But if you're getting over here minus 85, then it's a problem because you're getting a lot of losses, and maybe you need to install another antenna or adjust the position of that antenna to cover this area based on your judgment. So that's why we do the continuous wave testing. It's also called test transmitter testing, to evaluate our design positions. So if our thought process cannot evaluate well looking at the design, because you don't know what kind of walls are there, what kind of structures are there, then you do this test transmitter continuous wave testing or test transmitter testing in order to finalize the antenna positions. So this is an important step which is usually followed as well. Okay. Well, how close two antennas should be from each other? They need to cover. So our objective is to meet the design threshold with installing as minimum antennas as possible, because antenna is a cost. So we have to have a good signal, installing as little as antenna as possible. That's our objective is. So how far the antenna can be, as far as possible. Will they interfere each other antenna? At the back of them, if they are connected with different cells, yes, they will interfere. But usually that is not the case. At one floor, all the antennas are connected with one cell. So they don't interfere because they are connected with the same cell. Okay. So why equipment room location? If you want to design from previous projects with Ericsson in Nigeria and Tigo, okay, yeah, means the reason they don't do the continuous wave test because they have an idea, or they just want to install more antenna instead of wasting time for, in their view, it may be waste of time to do the test transmitter testing. It all depends how effective that method is. If you need it or you don't have an idea of the structure, then you need it. Usually it's not done at every place, only at the places where the engineer have the confusion and they want the accurate results in order to place the antennas over there, then they go for continuous wave testing. It doesn't mean like if there are like 40 antennas, I will do the the continuous wave testing for all these antennas? No, I will do the continuous wave testing for only the antenna where I need confusion, like this antenna. Is it effective to install an antenna over here? If I want to, because it's a directional antenna, am I getting the coverage over here? Yeah, or over here, I'll go put a test transmitter with a directional antenna and see over here. So it's just for it's not done for all the antennas, but it's a process which we should understand and we should utilize whenever possible for the best achievable design. Now, from the perspective of passive system, equipment room location is very important. Why? Because as the longer the distance between the node B or E node B and the antennas, there will be greater losses. So you will have to go and install an active system instead of passive, because the higher their losses are high. So usually it's very critical, and the design which we have been following, not in USA but in UAE and other places, even in Nigeria, the criteria, because I have worked in Nigeria as well. So the criteria basically always was followed that to install a passive system as much as possible because it's more cost effective. In order to do that, you have to have an equipment room which is closer to antenna. So when you look at the building, you say, okay, I will install. So ideally, I will not install, if it is a 50 floor buildings, I will not install a equipment or at the basement or at the top floor. I'll install antenna. Sorry, I'll install node B, not antenna. I'll not install node B at the bottom or the top floor. I will install node B at the center floor. So I can, the same node B has a minimum possible distance from the top floors and the floors under it. So that is the ideal way. But sometimes you're not able to negotiate with the owner the equipment room location. Maybe I get more than one equipment room location for a big building as well. But it is very critical. We should understand that it is very critical to have a good equipment room or room location in order to avoid an active system, okay, which requires negotiation with the owner and approval of the owner for that building for sure. So once we have done this, which is called floor plan, once we have placed our antennas, we are happy with our antenna design, they look good to us, we said, okay, this will be the placement of our antennas. We show it to the owner or building owners, they approve it, everybody is happy. Then but to reach over here, we had negotiations on equipment room, we had a continuous wave testing if required to finalize this floor plan. Okay, so on the paper it's very simple, just placement of antennas, but it may be a lot harder than what it seems. Okay, so once we arrive at the floor plan, we move to the design plan. What is design plan? Design plan is actually the link budget, the calculation of the cable lengths, what kind of antenna we are using. It's a complete link budget and the schematic drawing of the connection. So it is the connectivity drawing of our DAS system, how we are connecting, and what is the power calculation or the EIRP for our system or at our antenna. So the design plan contains all the components in the DAS system, all the antennas, if it's active, all the active components, if it's passive, all the passive components, and is the basis for design plan. And on the basis of design plan, we will do our link budget completely. Okay, design plan is also called schematic drawing sometimes, but in Ibwave design plan, the terminology used for it is design plan, and shows all the components of DAS from equipment to antenna. So all the components between equipment, which is node B or E node B, to antenna are present on the design plan. Design plan is very a basis of link budget calculation. So design plan, based of design plan, we do our link budget. In fact, in case of Ibwave, you see design plan, the link budget calculation are done or displayed on design plan itself in order for the better pictorial view. It makes make it very easy to visualize if one cell branch of the cell or the whole system needs active components, because we can see, okay, these antennas, this cell is connected with 15 antennas. Out of these 15 antennas, these 4 antennas have a EIRP of below the threshold. The rest of them are good. Then we can install active component only at that part as well, or for only the branch going to those five antennas as well, saving us the cost. There are other possibilities as well. It is a very important reference point to make the design changes after implementation. If you want to make any changes, all the link budget calculation, the itself, the cost or money or dollars is associated with the change. Everything is evaluated based on the design plan because it's very quick to grasp. Design plan is very important for radio frequency design sheet document, as it is about all the components and how they are connected. So our RFDS for DAS or distributed antenna system has two diagrams. One is our schematic diagram, how the equipments are connected, and our Ibwave design itself. And second part is called head-end diagram. We will study that. We'll study that when we study the RFDS for DAS system. So it's a head-end diagram. So these are the two diagrams. We call it a head-end diagram, which you also can call plumbing diagram. It just shows how to connect your node B with the DAS. And the DAS on that diagram is shown as a box. And there is a complete schematic diagram of the DAS after that, which what we are doing is basically working on that schematic diagram right now. Using Ibwave, we can create the design plan and floor plan very quickly. So that's the advantage of Ibwave. These two things can be done very quickly and effectively, and change on the floor plan are directly reflected on the design plan. So what happens is, if I remove, in case of Ibwave, if I remove one of these antennas on the floor plan, that will automatically change on design plan. Design plan looks something like this. This is just a rough example of a design plan. Okay, not exactly, but just a rough example of a design plan. We will see actually the design plan, how it looks like in next session. Even the slides to come in this session as well. Okay. So this is how our design plan looks like. If you see, these are the splitters, 3-way, 4-way. This is the passive system, because there is no active component. For the simplification, this is our node B. This is our first cell. This is our second cell. It's going in this combining and duplexing unit to combine it. It's a two-way. These are combined. So on both the channels, both these cells are there. Both these TRUs are there over here. So both the cells are on both the lines. So all these are transmitting on for both the cells. Okay, you can say it's carrier 1, it's carrier 2. So both carrier 1 and carrier 2 are combined and duplexed. So when they are going in here, carrier 1 and 2 is on this line and this line both. So it goes in the whole system. So every antenna will be transmitting both carrier 1 and carrier 2, if you assume this is carrier 1 and this is carrier 2. So you will have been, so usually important thing is, these are splitted. This is a two-way splitter, then we feed three-way, because overall number of antennas we had was from 25 to 35 floors, which is about 10 floors. Each floor had 4 antennas. Okay, so 4 multiplied by 10 is like 40 antennas. So we had to split our signal. It's just an example. I'll go through a simpler system as well. So we had to do the splitting. So if I start to do a simple calculation over here for you guys understanding, let's say this is a 43 dBm, 43 dBm from here, 3 dB of loss in CDU. So I got 40 over here. So I'm 40 dBm over here. So 40 dBm will be splitted. So it will be on this line and this line. Can somebody tell me what will be after the two-way splitting? What will be the power on this line? What will be over here? And what will be the power on this line? Can somebody tell me? Yes. Okay, so it is 3 dB, it will be 40 dB, correct. Okay, so this is 40, this is 40. So then I'm splitting this again. I want to calculate the power for this antenna. So all the antennas are go. So this is a three-way splitting again. So this is 40 watts because it's splitted. We did the splitting. So this was 40 watts. This 40 watts becomes 30 watts over here because this is a sorry, not 30 watts. This 40 watts become 37 37 dBm over here. Okay, so this 37 over here, this is a three-way splitting. So three-way splitters have 4.5 dB loss. So let's assume it is 32.5 and then again 4.5 loss. So this is 27 4.5 sorry 28 over here. So 28, then we have a four-way splitter, which means 6 dB loss. So it over here we'll getting a ERP of EIRP. EIRP in short is also called ERP or ERP. We'll be getting a ERP of 22 over here. Okay, so 22 ERP is very good. Okay, it's considered very good. Now remember what is this value? So this is value. I said this whole transmitter is 43. So I know 43 or 46 is usually the total power of the cell. So I did all this calculation based on the total power of the of each cell. So this is a 43 dBm and this is 43 dBm. So so in Ibwave, what they call it, these are two carriers, right? Carrier 1, C1, C2. But in Ibwave, this is called per carrier, power per carrier. Okay, so this is power per carrier basically. Okay, so power per carrier. So this is, since we started our calculation on the basis of power per carrier, so this ERP is power, will be called power per carrier ERP. Okay, carrier ERP. Okay, so this ERP is power per carrier. Power per carrier is also called power per channel. Okay, so we can also call this power per channel. Remember this, power per channel. The reason this is power per channel, the reason this is power per channel is because we started our calculation, we took this 43 dBm, which is the total power of this carrier 1 or C1. So since we started our calculation on the basis of complete power, this is called power per channel or power per carrier, ERP. So the calculation we did for ERP or EIRP was based on power per channel or power per carrier. Ibwave call it power per channel. Okay. If I would have done this calculation based on CPitch in case of UMTS, so I know the CPitch is 10 dB less. I have configured my CPitch for this carrier 10 dB less than this, so it will be 33 dBm. Okay, so ultimately this is my EIRP based on the power per carrier. So what will be on the basis of CPitch? Can anybody tell me over here? Instead of this 22, what will I get? Yeah, simple, 12. Okay, I'll get 12 dBm. Why? Because my CPitch is 10 dB 10 dBm lower than my total power of my carrier. Okay, that's what I know. 10% is. So 43 minus 33, no, it's 12 basically. Or yeah, ERP. Whatever ERP I got on the basis of power per channel or power per carrier, I will reduce 10 dB because my CPitch is usually 10 dB. Or let's say my CPitch is not 33. My CPitch is, this is 43, but my CPitch is 30 for any reason. I have configured my CPitch to be 30 in UMTS. So if I have configured it to be 30, then the difference between my power per channel and my sippage is 13 dBm. So I will deduct 13 in that case from here, which will make it around 9 dBm of ERP. Okay. So this is basically this is a schematic. We can do it calculation on the basis of total carrier power, which is called composite power. Okay, we can do it. So all this calculation was done on the basis of power per carrier. So power per channel. Okay. So and we understand what is power per channel, and we understand what is carrier power. What is EIRP? So we understand now how to calculate ERP or EIRP, or which is called power per channel, and which is also seepage power, and how to calculate ERP for seepage power. So we understand those things. Only thing which is remaining is the concept, which is a composite power. Okay, composite power is not so much different or difficult. What composite power is, this is 43 dBm for carrier 1 or 43 dBm for carrier 2. What composite power does is add these two powers and say this is 46 dBm. Okay, 46 dBm, and this is called composite power. So composite power. Okay, so whatever your EIRP calculation for power per channel was, you will add 3 dBm, so you will get composite power. You will subtract about 10 dBm, whatever your difference between total power and seepage power, you will get ERP for seepage power. Okay, so this, it's simple. You do the calculation on basis on one, and you add or subtract, and you start to get the other results. So it's not so complicated. Okay, guys.